11.4 Solving nonlinear systems. Alright, we've done linear systems so far, and that's been fairly straightforward. We should be able to solve some nonlinear systems, and a nonlinear system would include some type of an equation with a variable that has an exponent different from 1. So, for example, x plus, we'll make one of these, 2x plus y equals a negative 3 is linear. But if my other equation was like x squared minus 2y is equal to 5, then the system all of a sudden became nonlinear because of this thing. Okay, they can be solved, similar methods as linear systems, so we can solve them graphically, for example, graphically, or we can do it algebraically. And that would imply that we're either going to use elimination, which is usually my favorite if I had to do it through algebra, or substitution. Substitution. So let's look at a couple. One of the things that you really should take a look at is what type of equation do you have before you start. So that gives you an idea of how many solutions could you possibly have. So for example, x squared plus y squared equals 13. Well, that is a circle. And x squared minus y equal to 7, that is actually a parabola. And if I think about these two shapes, and I draw a circle, and then I draw a parabola, and let's just draw one that goes normal, then you can see that I could have 1, 2, 3, 4 solutions. Now it is possible to have less. I mean, it could touch here. I would only have one, right? The parabola could drop and actually touch here, and I would have 3. The parabola could be completely above or completely below, so they could not have any solutions at all. Can we get 2? Yeah, I think we can get 2. If I would put the parabola on the outside like this, we can have 2. And so there are a number of cases here that are possible. So look for that in terms of, what can you expect. So when you get answers, you shouldn't be surprised if you get more than one answer, for example, in this case. Hopefully they'll let me do that. Nope. Okay, I don't need this stuff, so let me erase this stuff. Alright. So how I'm going to solve this? Well, it's sort of hard to see what's best, and I've mentioned it over here. You just have to do this and try it and see what happens. So for example, something here that might look good would be to say, well, this means that x squared is 7 plus y. That's great. I've solved for x squared, so plug it in over here, right? So I get x squared is 7 plus y. Wow, it's tired. I'm tired. Sorry, I get 7 plus y squared is equal to 13. And I can rewrite that a little. Y squared plus y, 7 here, 13 there, so minus 6 is 0. And you know what? That's actually factorable. And so I did something that worked, which is great. So there are two y values that I then need to check. I need to plug these in over here and see what happens. So if y is a negative 3, right? So if y is a negative 3, then x squared would be a negative 3 plus y, or sorry, 7 plus a negative 3. So x squared is equal to 4, and that would give me plus or minus 2. And don't forget plus or minus. So right now my solution set includes 2, negative 3, and a negative 2, negative 3. Okay, how about here? If I plug in the 2, I get x squared is equal to 7 plus 2. So that means x squared is 9, so x would be plus or minus 3. So there are more answers. There are 2 more answers. So at 3, the y would be 2, and at negative 3, the y would be 2. So 4 answers. Okay. I do want to do this particular one graphically, so let's see what I can make off that. I should probably mess with these equations a little bit over here. let's see, I need to rewrite that one a little bit more. So if I bring the 7 back over here, then the y is positive, right? So it would be y equals to x squared minus 7. So that is a parabola with, on the y-axis, that goes through 0, negative 7. So the vertex is at 0, negative 7, and then it goes up. So if you think about that, it looks a little like this. So through here, and then it goes up. Okay? Circle here is already written in a form that I can tell you that the center is going to be at 0, 0, and that the radius is the square root of 13. Now the square root of 13 is going to be close to 3.5, so let's say it's 3.6. The reason I say it's close to 3.5 is because the square root of 9 is 3, the square root of 16 is 4, and 13 is 4 away from 9 and 3 away from 16, so it's just past 3.5. Okay, well that gives me an idea where I need to be over here. So I need to be able to be all the way down to negative 7. I need to be able to go up to a y of 2, and that should take care of it. So let's see. Yeah, I'm going to have to erase this. I'd like this to be in blue. So we'll go over here. And then we're going to tick mark. And we'll have to go down to negative 7. So 1, 2, 3, 4, 5, 6. Negative 7. So 0, 1, 2, 3 this way. 1, 2, 3 that way. So we'll see where we are. So if we go 1 each direction, we're up 1 over 1. The next one should be 1, 2, 3. Now it should be over here. So over here. And the next one should be up 5, right? So 1, 2, 3, 4, 5. And over here. And over here. And that was actually a point of intersection, because that's negative 3, 2, and 3, 2. So that would be this one and this one. Okay, the circle, the center was at 0, 0. And then about, what was it? A radius of about 3.5. So let's see if, how do the circles work here? Okay, so I should be able to start over here. The radius of about 3.5. Right? So that looks like this. Not bad. Because these were also supposed to be on there, right? These are also intersections. So there's the circle. And the parabola looks like this. And there we go, graphically as well. Okay, let's do another one. Oh, wow. I'm not sure what this mess is over here. That actually is a circle. I have a square with an X, a Y with a square, and then the 2 somehow becomes a radius. So this is a circle. I have no idea what this is right now. Okay, so let's see, how can we solve it? Well, we're going to solve this algebraically. And I don't like this over x thing, so I'm going to just multiply everything by x, which means that x can no longer be 0, or, well, it shouldn't be 0 anyway because you're dividing that over here. So let's see, what do we have? We have x squared plus x plus y squared minus 3y plus 2 is equal to 0. And here when you multiply out, you get x squared plus x plus y squared minus y equals 0. So that's also actually a circle, the second one. It just has a hole at 0. Okay, so this is going to end up being a hole at x is equal to 0. I'm not sure what the y values would be, but actually you just plug it in here and you can see what the y values ought to be. Okay, let's solve here. So these look all the same, so let's subtract, because that's 0, 0, 0. And a negative 3 minus a negative 1, it's actually a negative 2, isn't it? And 2 minus 0 is just 2. So that means 2 is equal to 2y, so y is equal to 1. And if y is equal to 1, then I can plug it in here, so then I get x squared plus x plus 1 minus 1 is equal to 0, 1 minus 1 is 0, so x squared plus x is 0, that's factorable, x plus 1 is 0, so you either get x is 0 or x is a negative 1. So the solutions, I said solutions, but this one's not allowed, right? The only solution that we have is a negative 1 and 1. So we have two circles that somehow only connect in one spot, when they're not. It'd be okay if they were tangent, but in this case they only go in one spot because it's 0. So let's see, that's 0, so at 0 we have a hole there. So that's going to be an intersection, and then here you basically get a hole. Okay, so like a, looks like a duck. Look back at it and see if you think it looks like a duck. Okay, how do I graph this mess? So you gotta complete the square in this one. Actually, on both. So it's x plus a half squared, and then here is y minus 3 over 2 squared. The 2 needs to be over here, so that's a negative 2, and then I have 1 over 2 squared, too much, so that's 1/4 over here, and then I have a negative 3 over 2 squared, too much, so plus 9 over 4. So that gives me a circle that looks like this. That's 8, right? Negative 8 over 4, negative 8 plus 10 is 2 over 4, which is a half. So this circle has a center at a negative half 3 over 2, and it has a radius of, I'm not sure if you guys can see that, let me erase that, and it has a radius that is equal to the square root of 1/2, so 1 over the square root of 2. And that's about 0.7-ish. Use a calculator for that if you need one. Okay, so that's the first one. That's this one. How about this one? So that looks a lot like that, except there's a small difference already here, so that's minus a half. And that's 0, so here you get 1/4 plus 1/4, too much. So we get the following circle equation, and a quarter is a half. So the center is very similar. It is at a negative 1/2 again for the x, but now the y for this one is only a half. So they're 1 apart that way. And this one has the same radius. It's the square root of a half, which is approximately 0.7. Okay, so let's graph that. Need a little more space. Do I have it? Yep. So on this one, I don't need a lot of space, but I want to give myself a slightly larger scaling so that I can actually see some stuff, because half's there. So if that's 1, that would be 2. So that's a half. That's a half. So that's 1. That's a half. 1, a half. And 3 over 2 would be 1.5, so I need to go a little bit more. Okay. First center, negative 1/2, 3 over 2. So that would be somewhere over here. And then the radius is 0.7, so it's a half, so I should be close to here. So let's see if I can grab my circle again. I can do it the same way. So I think it's going to look a lot like this. Okay. The next one has the center at a negative 1/2, 1/2. So if this is 1.5, so 3 over 2, then that's 0.7-ish. So the center for the second one is actually just below this one still. And then they intersect sort of here, but that's supposed to be a circle. So I'm going to make that, or a hole. So if you go a half this way and then that way, that means that your second hole would be here because it's a circle and everything is the same distance. So my second circle looks like that, and then the intersection was at a negative 1, 1. So negative 1, 1. So that would be here. So let's see if I can make a circle that goes to those points. And that's not bad. And that one makes sense as well. So there's your picture. Okay? So graphing it here can be somewhat challenging. Maybe at some point we can do this with some technology. That's another lesson of itself. Okay, then we get to a difficult word problem. And I say difficult because, quite honestly, I also had to cheat a little here in terms of looking at the solution in the book. But it does show some things that are sort of neat and that are interesting, so let's see if we can run through this. So in a 50-mile race, the winner crosses the finish line 1 mile ahead of the second and 4 miles ahead of the third, assuming each runner maintains a constant speed throughout the race. So that means that each runner maintains his or her own constant speed. So they don't have to be the same. Clearly they can't be, otherwise they don't finish at the same time. And then ultimately we want to know how many miles does the second place runner beat the third place runner. Okay, so here are some things that we know. We know that that's supposed to be a circle, but we know that the 50 miles is, well, let's backtrack actually. We know in general that distance is the speed times the time, right? So that's what I'm going to write my equations based on. I know that the winner ran the 50 miles in his or her speed and his or her time. At that point, the second place runner was only at 49 miles. So that's the second place, and that's the same time. And the third place runner was only at 46. And that's still all at the same time. And we also know that the second place runner does finish the 50. So we know that there's that second limit, or sorry, speed goes with a second t. And finally, we know that the thing that we're interested in is the distance between the second place and the third place runner. Well, the second place runner, this is the second runner, right? The second runner runs 50 miles. And the third place runner runs that velocity times the second place runner's time at that moment. So these are the things that we know. Then somehow this mess I need to solve for. Okay? So how do we do that? Well, let's start looking at this one. So and this is why I cheated and I looked in the book a little to get an idea. So I'm going to start with that one, and I'm going to multiply that by t1 over t1. That would give me 50 minus v3 times t1. I'm going to change that, and then times t2 over t1. So I'm interchanging these two. The reason I do that is because I know that the velocity of the third runner times the first time is 46. So I can place 50 minus 46, so that's now replaced with 46. And then I'm left with t2 divided by t1. I can write expressions for t2 and t1. If I know that the 50 miles is the velocity times the first time, and t1 is 50 divided by v1. And if I know that 50 is also equal to, what am I looking for? T2, right? And that's the only T2 that I have. So I need V2 T2, then I get 50 divided by V2. So let's see where that brings me. That is 50 divided by V2, and then dividing by that is multiplying by the reciprocal. So I'm going to multiply by 50 this one. So that actually gives me 50 minus 46 times the velocity of the first divided by the velocity of the second. Well, those I can actually solve for, and I can do that right in here. I know that V1 is 50 divided by T1. Now that V2 is 49 divided by T1. And it's, the reason we do this here is because that's the same time, right? So we're going to plug that in. So what do I have? I have 50 minus 46, and V1 is actually the same as 50 divided by T1. And then we're going to multiply by the reciprocal of V2, and V2 was 49 over T1. So that becomes T1 over 49. And that goes away again. So that we have 50 minus 46 times 50 divided by 49. And that means that the distance between, and this was defined as the distance between the second place and the third place runner. So that distance is actually 3.06 miles. And that's it. Thanks.